Good morning, good afternoon, everyone. Thanks for joining us. We're going to give a couple of minutes for folks to get signed on, and then we'll get started here. Since we've got a few things to start with on housekeeping, I'll go ahead and start. Um, Thanks for joining us today, taking time out and joining us on our second of four webinars around CTM technology and exotherm solution. Um, We're planning on presenting for about 25 to 30 minutes and rolling up with question and answers. You can ask questions by clicking on the icon in the top right hand corner, a little question mark box inside of a chat window. We will be fielding those throughout the presentation, and we'll try and answer as many of those questions as we can at the end. And anything that we don't cover, we will get back to you via email. We will have this presentation available for you to download and review here in a few days' time. We'll follow up with an email. I'm Brian Tian. I'm one of the segment leaders for Exotherm in the Americas. And with me today, we have a little bit of a change. Thomas, you want to go to the next slide here? Originally, we had planned on Mr. Neil Riley joining us, but just a last minute change here. So Thomas Schmidten is presenting from EMEA group. He is our segment or our leader for that region, and I will let him introduce himself.
Thank you, Brian. Okay, so good morning and good afternoon, everyone. Happy to be jumping in for Neil today and meeting and discussing with all of you. I'm leading Exotherm's activities in Europe, Middle East, and Africa.
So again, this is the second webinar in our series of four. The first one we had I believe it was about 6 weeks ago, future-proofing your critical electrical assets. Today, we want to talk more about the technical applications and considerations of applying continuous thermal monitoring to your electrical assets. And then we will actually lead into the third and fourth that are forthcoming in the next couple of quarters. So I will leave it to Thomas to go through some of the industry trends, drivers, and then considerations for application.
All right, thank you so much, Brian. Yeah, thanks again for connecting, everyone. Let's start with framing the topic around looking at, like Brian was saying, some key industry trends and drivers that are shaping all of our activities and that are resonating feedback in all of the customer discussions that we're having. So first of all, when listening to end users and operators, it's all about how to keep the system up and running and how to run more reliable, resilient operations. Many end users and operators today are still running their systems blindly to failure and are surprised by unplanned outages occurring, losing the system, everybody's huddling and scrambling to get the process up and running again. And it's about step by step merging from running to failure or time-based snapshot in time inspection and maintenance activities through confidence and comfort up the line towards condition-based and finally towards 24/7 continuous online monitoring for operations optimization. The second thing that resonates in customer discussions is safety, always a top priority. Still today, too many people get injured or there's even fatalities when operating power systems. Electrification hazards, internal arc flashes are still too predominant in running power systems. So it's all about keeping the teams, keeping people from harm. And the third area of focus that resonates in customer discussions is around sustainability and circularity. It's about using the existing assets, sweating those assets longer, so extending their lifetime, doing more with less, directing capex and expenditures in the right pockets for ensuring the uptime reliability, then the return of investment through smart decisions in order to also reduce carbon emissions and the greenhouse gas exposures. So it's all about building and retrofitting power systems for their lifetime extension and optimizing them as we go. When doing that, it will save natural resource extraction and formulation in the first place. So less iron ore or copper will need to be mined, less steel will have to be produced or aluminum to be smelted. In consequence, then on the manufacturing side, with less equipment that has to be replaced, there's going to be less replaced equipment manufactured in different plants, reducing the CO2 emissions from that end, and at every step of this supply chain, avoiding the transportation costs related with it, and in consequence, the carbon emissions that come along with it. So when we walk through this webinar, let's think about these three key drivers: uptime and reliability, safety, and circularity and sustainability. And when we survey the end users and listen to what they're saying, around 70% of them still experience unplanned outages at least once a month today. And an outage typically costs somewhere beyond 100,000 US dollars per hour of that downtime. In some cases, even more than $1 million per hour. So unplanned outages are still a massive operational factor in power systems operations or industries who use power systems. While the same percent of companies surveyed still report that they're using run to failure or time-based maintenance strategies, so snapshots in time. Whereas most of these organizations have realized that there's, based on technology and innovation, a smarter way to harness this topic and direct investments towards reliability and resilience and maintenance only within the next couple of years. So we're really at a shifting point of time in how to engage with power distribution systems. Now, with this introduction, let's take a quick look at how the discussions in the industry and the thought processes shaped over the last decades around uptime and around personal safety, just for setting the stage for the topic of this webinar. So when looking at that, I'd like to categorize the quadrants into the time after a fault occurs and the time before a fault occurs, and then split activities and discussions into whether they're rather passive approaches or rather active approaches to the topic. And since decades, the industry has been putting their heads together and designing and type testing, manufacturing and rolling out equipment that is safe by design. Arc-proof equipment, in IEC they call it internal arc classification or qualification. It's basically around getting equipment designed with pressure relief flaps and ducts and chimney systems for keeping people safe, the operational level safe, and guiding, in the case of an internal arc fault, the ionized flames and the hot plasma and the pressure wave away to a safe area. Then the discussions swapped a little bit more around what can be done before a failure even occurs in the first place. And that's when the discussions around inspection and maintenance strategies entered the picture. Time-based inspection and maintenance, and then risk-based inspection are still the predominant ways of engaging with power systems, still on the very passive route. So about 15, 20 years ago, around personal health and safety, technologies around active arc limitation or mitigation systems emerged. It's about identifying an internal arc occurring in the equipment, for example, using light and high current information, leading to an immediate circuit breaker tripping, or in a next stage, triggering a device that takes the basically three-phase voltage earth connection to the ground for reducing the incident energy from extracting and expanding the volumes and burning the metals and epoxy in the first place. Not only keeping people relatively safer, but also limiting the damage to the equipment. So in consequence, the degree of servicing and maintenance or replacement works that would need to happen. But still, all of these approaches require corrective maintenance. You're surprised by arc flashes from occurring while assuring safety and uptime to a certain degree. And then the discussion moved towards that first quadrant, because none of these other approaches predict and prevent failures from occurring in the first place. And here the discussion circled around, well, the main physical causes for arc flashes. On the one hand, continuous partial discharge sensing, especially on the medium voltage and high voltage side, for identifying any noise or any activities going on before the strike would break through. Second area has been around continuous switchgear room ambient condition monitoring, or inside the e-house, capturing temperature, humidity, unlocking dew point calculations, and so on. And then thirdly, the discussion has been centered around continuous thermal monitoring. So this is where the core of the webinar today sits. And continuous thermal monitoring is responsible for 1 out of 3 failures in operating power systems. Yeah? Failures due to loose joints and connections, cables becoming loose over time, or the bolts that are holding bus bars together becoming loose over time due to temperature variations, due to vibration or other activities. And then in consequence, the diameter decreasing, the resistance increasing, the temperature increasing, which leads to accelerated aging behavior, and then finally electrical breakthroughs, fires breaking out, and internal arc flashes occurring. So it's about the maintenance strategy evolution here, moving away from that vicious cycle of being surprised by outages and being reactive in operations, all the way step by step towards predicting and preventing failures from occurring in the first place, for running resilient operations and for keeping people safe. And the key to that is industrial Internet of Things enabled continuous condition monitoring, unlocking predictive maintenance of the power systems we're operating, or everyone's operating, which ties back to the opening 3 trends I was mentioning: unlocking improved performance, the operational efficiency through digitalizing assets and increased understanding, and increasing safety for all of the people around. But when we think about this continuous thermal monitoring landscape, the sensor solution options out there are very broad and vast, and it's hard to wrap your head around what is the differences, what's the implications for design and engineering, and what's the implications for operations. Yeah? How to get a grip on this vast landscape. And just to select a couple of sensor solutions for catching hotspots, as an example. There's many differences on many levels. For example, in terms of their power fetching mode, or the way that they receive or take power. There's, for example, inductive energy harvesting technologies, or ultra high frequency wireless power supply tappings of sensors. There's thermal non-powered sensors as well. From a temperature measurement method, there's differences. is a sensor built in and actually measuring temperature, or is it a simulated indirect indication of the temperature, for example, via frequency change or via looking at wavelength? There's differences in sensor sizes, large, small, medium ones. What does that mean? Having a sensor head at different positions of different sizes. There's different installation methods, finally. Sensors that have to make contact with the power parts, with the main current carrying path, and sensors that are of non-contact, located in a safe distance away from the metering points, measuring points. There's differences in installation position. Some can be looking at bus bars or terminals, output terminals only. Some can be in flexible positioning, depending on the type of technology. There's differences with regards to the stability of communication. Is it a digital transmission? Is that one hardwired or wireless? I mean, with regards to causing false alarms or subject to interference on the way. And finally, there's differences with regards to sensor life. Is it a complex circuit or is it a simple circuit? Is there exposure to vibration, mechanical stress, or any of these things during the lifetime? And what does that mean? Brian, what do you think about this broad and vast landscape?
So we've kind of gone into a bunch of the whys, and I think the overall message here is we're trying to minimize the degradation of these electrical assets over time, provide safety, provide uptime, drive that efficiency. So let's get into some of the some more of the technical aspects and differences between these technologies, and maybe dive into those the communications, the communication platform, the sensor power, how we actually look at these hotspots, and then where and how we apply these.
Exactly, exactly. Very good. Thank you, Brian. That's a great trigger here. Um, when when thinking about this broad and vast technical solutions landscape that we're facing with regards to temperature sensing, a good way for thinking about technical considerations for orientation is along three lines. First, I think, like Brian said, it's about how does the sensor communicate? And on the left-hand side of the slide, you can see that there's some aspects around wireless sensor communication. And on the right hand, wired sensor communication options. So let's look at that with regards to the attributes of antennas, of communication, and of reliability. So with regards to wireless sensors, typically when you're looking at the pictures at the bottom of the slides here, when there's a transmitter and a receiver, well, typically there's going to be receiving side antennas required for catching the temperature measured at the meter at the measuring spots in the first place. Often there's multiple antennas required, sometimes inside the low voltage compartment, sometimes even located within that same power compartment. And the antennas themselves, while this is the wireless sensor connection, are on the other hand then wired themselves. So the wireless piece is really only a couple of inches, maybe just a few feet. There's differences with regards to transmission distance considerations, right? How far away can the antenna sit? Or how many must you consider given the amount of sensors that you need for monitoring every critical site-made connection inside the lineup or in the equipment? Then wireless communication always presents a cybersecurity risk. There's segments out there in the market who don't want to even allow any cybersecurity openings for entering any part of their systems. So that's an aspect to think about. Then different technologies have different numbers of frequencies that can operate in. For example, depending on the number of sensors that you will want to place, might there be overlaps? Might there be cross-talking or any sensor identification issues? On top of that, there's the risk of compromised signal due to electromagnetic interference, also depending on how will, for example, compartment cladding or compartmentalization of different parts of the lineup affect that transmittability. Finally, there's mounting surface installation challenges. Some of the antennas, for example, are magnetically connected to the power chambers. And it's a question, how good is that magnet going to be on that surface inside that powered up compartment? And might that not also present a risk sometime down the life? Finally, with regards to wireless sensors, they're quite easy to install, both in the factory as well as in brownfield. For example, watch strapping them around the main current carrying copper bars, and then programming them to speak with the antennas accordingly. On the other hand, when it comes to wired sensor connections, well, it's a hardwired solution, so no antennas are required, where there's no distance considerations or communication considerations with regards to frequency or sensor identification that needs to be regarded. Yeah? When things are hardwired, there's no cybersecurity risk. It's a fit and forget technology, which also doesn't have any of these surface mounting challenges, since typically the wires would be guided in the safe wireways like any other control wiring or auxiliary wiring. Certainly, on the other hand, when having a fully hardwired solution, well, that degree of additional wiring and labor related to it will be needed. Let's move on from the first technical consideration, the sensor communication piece, to the next angle of consideration. Let's think about sensor powering. And how are those sensors supplied, and do they even need to be supplied? And let's look at powered sensors on the left side, and then non-powered or powerless sensors on the right side. And think about, what does that mean with regards to calibration? What does that mean with regards to power supply, for example, using batteries? Some of the solutions out there come powered, for example, PT100 sensors or other similarly laid out technologies, who will, whenever where they need a current passing through in order to monitor or measure the temperature in the first place, require an amplifier. And whenever there's an amplifier, you're introducing drift. Whenever there's drift, there will be the need for calibration over time. So you're actually building in a weak spot to the power system that will be subject to regularly engagement and inspection and calibration, which itself will require shutdown of the respective equipment, on the one hand. Secondly, you will have to be in a position to reach each and every one of those sensors, no matter where in the lineup they happen to be placed. With regards to battery, well, battery-powered sensors are themselves subject to regular inspection or maintenance or interaction activity. A battery lifetime is somewhere between 3 years and 10 years. In any case, while equipment is built for 25 years or 30 years or 40 years, that you will have to access those spots in order to get those sensors to fire up and start communicating again in the first place. Moving to the right side of the slide, powerless sensors. Well, when there's sensors that derive their power from the source they're monitoring and don't need any auxiliary power supply through battery or any other means. When there's no power needed, there's also no drift and no calibration needed, which means no engagement for inspection or for maintenance activities, which results in uptime. When there's no battery, there's no replacement of that battery. And again, no engagement with these powerless sensors required. This is the fit and forget type of aspect. Moving on from the sensor powering dimension to the third technical consideration for orientation, it's around sensor placement. And sensor placement, if you look at the landscape, has offerings around sensors that make contact to the main bus bars or to some of the breaker parts. And then there's sensors who don't make contact to any of the power carrying parts. Let's look at those ones with regards to installation methods, with regards to what does that mean for commissioning and testing, and then finally reliability as well. So starting with the contact sensors typically need to be mounted on a bare metal surface. For example, with regards to energy harvesting, for firing up and getting the power that they need in an inductive way in the first place. They typically don't operate in consequence on insulated buses or painted surfaces or taped surfaces, but they obviously need the necessary inductive connection there. Some solutions are fixed under bolts that are also holding together bus bars or fixating cables on the cable termination side, which will require different torque settings wherever those sensors are placed. The other methodology of installing contact sensors, for example, is using bands or Velcro tapes. Some are clipped or even cable tie fixations that introduce themselves possibly an insecure attachment over time, which might face longevity issues and become a maintenance topic. Yeah, what if a sensor becomes loose over time? Well, if the energy harvesting sensor loses the connection, it powers down, it doesn't communicate anymore. And eventually, if it doesn't communicate anymore, you're going to have to go there, restrap it in order to even have it fire up again. Or even worse, what if the cable tie, due to vibration or temperature, or whichever externalities, finally loses connection, just drops inside the power equipment into one of the power compartments. The other thing to think about is with regards to be fully commissionable at site, or must they be placed and then connected with regards to configuration and communication during installation and commissioning at site? Yeah. What does that mean with regards to testing them only when the power is fired up? Because otherwise there's going to be no energy harvesting or no inductive power source for having them start communicate in the first place. And finally, there's a dimension with regards to humidity, dust, and dirt inside switchgear and other equipment. Wireless sensors, if there's a dirt layer between them and the bare metal surface, might lose connectivity and communication. On fiber optic solutions that are bolted onto bus joints or cable connections, you might be introducing, if humidity, dust, or dirt settles, a potential arc path along those lines, or you might introduce issues with regards to clearance topics. On the other hand, let's take a look at contactless sensors. Well, when sensors are not in contact with the powered conductor, there's no issues with regards to sensors becoming loose, becoming subject to temperature rises and drops and all of that. It can be pointed in a flexible way at insulated buses, at heat shrinks, at taped buses, or at even painted surfaces, and ensure accurate temperature readings. It doesn't require, since it's a contactless in a safe distance placed location, to undo any good bolts on the bus bar joints or the cable connections for fitting sensors, but ensures the right torque that this joint needs also for ensuring the bracing during short circuit conditions is met. With regards to commissioning, typically contactless sensors can be fully commissioned at the manufacturing plant before the equipment is shipped to site and then finally installed and tested. And with regards to reliability, there are sensor solutions out there that, due to being contactless, require no maintenance or repair, in consequence also no replacement during the lifetime of the equipment, which means you're not introducing a piece that needs to be eventually interfered with during the lifetime of the equipment in the first place. So the three technical considerations: communication, wired or non-wired. The other lighthouse for orientation is with regards to powering, powered and unpowered. And the next one is with regards to the placement. of using contact sensors and contactless sensors. And using these angles will already help you get a good understanding with regards to the implications of this vast and broad landscape. Brian, over to you.
All right, sir. Thank you very much. We'll recap this here in a second. We have some questions coming in. Before we get to those, we do have some exciting news and a few things to share with you. Um, and Thomas, I'll let you talk about those two things with our virtual showroom. And there's some talk of maybe an acquisition of Exertherm not too long ago. And then, like I said, I've got a few questions here from the gallery. Again, anybody, if you have questions, please submit them up through the question mark box at the top right-hand corner, and we'll do what we can to get to those.
Okay, great. Thank you, Brian. I promise to be quick, okay? So, first of all, stay tuned. In just a couple of days, the Exotherm virtual workshop is going to be launched, which will take you through the complete powertrain of applications across medium voltage and low voltage switchgear and motor control, across transformers, across PDUs and UPS, and also bus duct solutions, tying all of these applications, all of these assets together, and how exotherm solutions fit across this complete powertrain, unlocking the uniformity of data, so creating the comparability of data in the first place, and again looping back to the introduction, 3 industry trends and drivers, ensuring an increased uptime and efficiency and resiliency of operating power systems, increasing safety, keeping people from harm, and unlocking ongoing value while using reduced resources to our end users, operators, and the complete ecosystem. So stay tuned for that news coming up. The second one that Brian was just alluding to is last month, an exciting announcement hit the financial markets, and it's been around Eaton Electric having acquired Exotherm. So in specific, Eaton Electric's power distribution components business bought Exotherm, which is Eaton's low voltage breaker, power meter, and other sensors, basically components business, that Exotherm is now in the context of being, in the process of being integrated to. This part of Eaton Electric sells to Eaton switchgear factories and panel builders and OEMs, and to non-Eaton panel builders and OEMs and system integrators, and the vast part of their portfolio through the distribution channel. So Exotherm is very happy around having found this great home. It's a setup where we believe in this broader context on stronger shoulders will be together with our ecosystem, be able to help our customers and the segments we serve in an even stronger way going forward. With that, I hand back over to Brian.
So just to kind of recover or go back over what we have talked about, the technical considerations that we really want to work with you, and we have to look at each one of these applications individually, is the type of sensors, the pros and cons for wired versus non-wired, powered, energy harvesting, or contact versus non-contact. All of this, again, to minimize that degradation of your critical electrical assets. Drive that uptime, reliability. Of course, safety is huge. And then the sustainability of not just the equipment, but the overall impact on the ownership of that equipment. So let's see. A couple of questions here. How is commissioning done for shipping splits?
You want to take that, or I shall take that?
I'll let you address that one.
All right. So it depends on which sensor technology you're looking at. Yeah, in the context of this webinar, it depends on the application that you're faced. Are we looking at a low voltage or medium voltage lineup, or are we looking at a dry type transformer or UPS? Yeah? So from exotherm's perspective, it still depends on the specific sensor solution, but in general, how does commissioning take place or testing take place? Exotherm sensors are vastly installed at OEM factories, at panel builders, because it's never going to be easier than getting the eyes and ears you need for continuous monitoring into the equipment than X factory. So I'm taking that case now. The sensors would be placed in a safe distance from main current carrying paths or the powered buses. They would be wired up to the data cards in order to unlock the alarms and then the communication piece, fully factory pre-assembled and pre-tested. Exotherm offers a sensor verification device that even without buses being powered up, will that the right gain factors and settings and configurations of the installation were done correctly. Then you would just daisy chain the data cards from shipping split to shipping split via RJ45 cables in order to unlock communication, but the complete sensor placement and pre-wiring and pre-testing is done.
We are getting some questions on the different types of sensors that Exotherm has, both in the IR and their contact sensor, cable sensor, thermistor type device.
Yeah.
I think that is something that we haven't delved into real deep in this presentation, but we do have, it's a long conversation. And like I said earlier, these are all individual applications that we need to consider, both whether it's a retrofit or new equipment.
That's right. Yeah, and basically there's a suitable sensor solution for every application along the powertrain. Yeah, so while I was speaking about medium voltage and low voltage switchgear and motor control and transformers and UPS, these sensor solutions equally apply to automatic transfer switches or to bus duct T-off boxes or any powertrain, any power distribution system application that you'd be faced with or that you would be looking at. We are happy to engage and investigate which one of these portfolio members is the best fit.
And following up to that, what kind of history do we have installing this around the world? And do we have any case studies that we can share? So I know we've got thousands and thousands of installations and hundreds of thousands of these sensors around the world.
Yeah, so Exotherm is actually the pioneer and the technology leader in the space of continuous thermal monitoring. The company was founded over 20 years ago and has been developing and shaping and creating this market to a certain degree. And we've been serving thousands of projects, yeah, with end users across data centers, energy, oil, gas, and chemicals, across critical infrastructures like airports, hospitals, skyscrapers, you name it. So let's reach out. We do have quite a database of case studies as well as segment-specific webinars and information, and segment-specific leaders like Brian. So let's pick up on that one and follow up one-on-one.
And then finally, future-proofing through IIoT was brought up, which leads back to, or points back to the previous webinar. But why use delta T instead of absolute temperatures? I think that's a great lead into moving forward, Thomas.
That is a great question, and I don't want to steal the thunder of the upcoming webinar in the second half of this year, because that is truly important, right? Sensor hardware and understanding the implications for operations is just one piece. But then, what do you do? Yeah, if you're already thinking about communication and powering and sensor placement, what are you actually measuring and how can you interpret it? And what do you need to do? And that's exactly where the importance of temperature comes in. Why delta T? Why is delta T, so the rise over the ambient, in connection with the load, so important, especially measuring delta T at low loads. Yeah, so stay tuned for the invitation for webinar 3 coming your way.
Excellent. That pretty much wraps it up on, we did have a few more questions that are going to be a little more involved. We will have to get back to those via email. Again, we'll have this presentation available for you to download here in the next few days. You will see emails coming from Exertherm, anyone who has signed up. I want to thank you for your time, Thomas. Thank you for jumping in here last minute as we had a change in presenters. So thank you everyone for joining.
Thanks for having me. Good meeting you. Have a good day, everyone. Thank you, Brian.
Thank you. Thank you.